Before a tunnel boring machine ever slices into solid rock, its story begins thousands of kilometers away in some of the harshest places on Earth. Imagine standing inside an enormous iron ore mine where haul trucks the size of houses rumble past every few minutes, carrying hundreds of tons of rock in a single load. Most people never think about this, but one of the world's largest TBMs can weigh more than 4,000 tons, and almost every kilogram starts as raw minerals buried deep underground. The steel that forms a TBM's gigantic shield begins as high-grade iron ore extracted from Australia and Brazil, where some deposits contain more than 60% iron before processing. Massive blasting operations break apart entire sections of the mine, while electric shovels load over 300 tons of ore into giant mining trucks. The ore then travels through crushers, conveyor belts, railroads, and cargo ships on a journey that can span thousands of kilometers before reaching a steel mill. Steel alone isn't enough. The cutterhead that chews through mountains depends on powerful alloy steels strengthened with chromium, nickel, molybdenum, and manganese mined across South Africa, Canada, Chile, and Kazakhstan. Engineers adjust these elements with incredible precision because even tiny changes affect hardness, toughness, and wear resistance. A difference of less than 1% can determine whether a cutter survives years underground or fails far too soon. Now imagine the cutter discs themselves. Each hardened steel cutter ring can weigh more than 250 kilograms, yet during excavation it pushes against solid rock with tremendous force. Special heat treatments transform the alloy into an incredibly hard surface capable of crushing granite while resisting constant impacts. Inside the factory, the deep roar of furnaces gives way to the sharp rhythm of giant CNC machines carving perfect circles from solid steel. Copper becomes the nervous system of the entire machine. Thousands of meters of heavy-duty electrical cables deliver power to motors, sensors, lighting systems, communication equipment, and hydraulic controls. Much of this copper begins its journey in enormous mines in Chile and Peru before moving through smelters, refineries, and wire-drawing plants that transform thick metal rods into flexible industrial cables. Hydraulic systems require another family of specialized materials. Giant cylinders, forged pistons, precision valves, stainless steel components, and advanced synthetic seals work together under pressures exceeding 350 bar. Every seal must perform flawlessly beneath mountains where a single leak could halt an entire tunneling project. But here's what nobody tells you: one tiny component can stop a billion-dollar machine in minutes. Moving all these materials is a massive engineering project by itself. Huge steel plates travel by freight train, ocean cargo ships, and heavy haul trucks before arriving at specialized factories in Germany, China, Japan, and Italy. Some individual components weigh more than 100 tons, forcing engineers to carefully plan every bridge crossing, highway turn, and crane lift long before transportation even begins. The environmental cost is enormous. Steel production consumes huge amounts of energy, while mining reshapes entire landscapes and requires vast quantities of water. Modern manufacturers reduce their impact by recycling steel, recovering machining scrap, and using electric arc furnaces powered by cleaner electricity whenever possible. Even so, building one of the world's largest TBMs remains one of the most resource-intensive manufacturing projects on Earth. By now, millions of dollars worth of raw materials from every corner of the world have finally reached one destination. Yet they still look nothing like the colossal machine that will soon tunnel beneath cities, mountains, and oceans. And this is where it gets truly extraordinary, because next these massive pieces begin transforming into one of the largest moving machines ever built by human hands. What happens next surprised even experienced engineers. Manufacturing process. The moment the raw materials arrive at the factory, the transformation truly begins. Giant steel plates, some thicker than 100 millimeters and weighing over 100 tons, roll into the production hall on automated transport systems. Overhead cranes move with incredible precision, lifting each plate into position while laser projectors map out every cut. This is where a mountain of steel begins to take the shape of a machine that will one day carve through mountains. Next comes one of the most dramatic stages in the factory. Computer-controlled plasma cutters fire jets of superheated plasma reaching temperatures of nearly 25,000 degrees Celsius, slicing through thick steel as if it were butter. Bright white sparks explode across the shop floor while molten metal rains beneath the cutting table. Every cut follows a digital model with millimeter accuracy because even the smallest mistake could affect the entire machine. Now the flat steel plates must become a perfect circle. Massive hydraulic rolling machines slowly bend each plate using thousands of tons of force until it matches the exact curvature of the TBM shield. The process takes hours, but the movement is so smooth it almost looks effortless. Most people never think about this, but the machine that digs perfect tunnels must first be built with almost perfect geometry. Once the curved sections are ready, dozens of robotic welding systems take over. Brilliant blue welding arcs reach temperatures above 6,000 degrees Celsius as robots move with incredible precision around the enormous steel structure. Sparks shower onto the factory floor while experienced welders continuously inspect every joint. Even with advanced automation, human expertise still determines whether every weld meets the highest standards. Welding creates internal stresses inside the steel, and those stresses must be removed before the machine can survive years underground. Entire shield sections enter giant industrial furnaces where they are heated to around 600 degrees Celsius for several hours before cooling slowly. Heat waves shimmer through the air as glowing steel gradually releases the stresses locked inside. What looks like a simple heating process dramatically increases the machine's long-term durability. Now precision replaces raw power. Giant CNC machining centers remove only tiny layers of steel from critical surfaces, achieving tolerances measured in fractions of a millimeter. Coolant sprays continuously across the cutting tools while lasers verify every dimension. The roar of heavy machinery gives way to the steady rhythm of precision engineering. This is where the heart of the tunnel boring machine finally comes together. Hundreds of cutter housings, scraper tools, and massive disc cutters are installed one by one using crawler cranes and hydraulic lifting equipment. Every component must fit perfectly because these cutters will eventually crush some of the hardest rock found anywhere on Earth. Looking at the completed cutter head feels like standing in front of a gigantic mechanical monster. Next, engineers begin installing the hydraulic systems that give the TBM its incredible strength. High-pressure cylinders, pumps, valves, and thousands of meters of hydraulic lines weave throughout the machine like arteries inside a living body. These systems operate at pressures exceeding 350 bars, generating the enormous forces needed to push the machine through solid rock. One tiny leak could stop everything. With the mechanical systems complete, thousands of electrical cables find their place inside the machine. Engineers connect powerful electric motors, sensors, cameras, control cabinets, and communication systems that allow every component to work together. As each connection is tested, indicator lights begin glowing across the TBM. For the first time, this mountain of steel starts to feel alive. Digging a tunnel isn't just about breaking rock, it also means removing millions of tons of excavated material. Giant screw conveyors and heavy-duty belt conveyors are installed behind the cutter head to transport crushed rock safely through the machine. During testing, artificial material flows smoothly through the entire system, proving that everything works exactly as designed. Now comes the moment every engineer has been waiting for. Overhead cranes carefully lift the gigantic cutter head, shield sections, backup gantries, and support systems into their final positions. Hundreds of workers coordinate every movement while laser alignment tools verify each connection. Piece by piece, one of the world's largest moving machines finally stands complete. Before the TBM leaves the factory, every major system must prove itself. The cutter head begins rotating, hydraulic cylinders extend with tremendous force, conveyor belts start moving, and thousands of sensors send live data to engineers in the control room. Everything must perform flawlessly because once this machine disappears beneath the ground, repairing it becomes enormously difficult. And just when you think the journey is over, the biggest challenge is still waiting, the moment this colossal machine meets solid rock for the very first time. Technology and quality. As the last major components come together, the factory enters its most demanding stage. Every movement now depends on precision, not strength. Hundreds of sensors, robotic systems, and powerful computers monitor every part of the machine before it can earn approval. Most people see a finished tunnel boring machine, but they never see the invisible technology that makes it reliable beneath mountains. The welding may be finished, but the inspection has only just begun. Robotic arms equipped with laser scanners travel across every welded joint, searching for cracks, voids, and tiny imperfections invisible to the human eye. Even a defect smaller than a grain of rice can grow into a serious failure after months of tunneling. What happens next surprised even experienced engineers. Instead of cutting the machine apart, engineers look inside the steel using ultrasonic and industrial X-ray technology. High-frequency sound waves and powerful imaging systems reveal hidden flaws buried deep inside the metal. The control room displays colorful digital maps showing every weld in incredible detail. If even one critical defect appears, the entire section returns for repair. Now every critical surface must prove its accuracy. Laser trackers and coordinate measuring systems inspect thousands of points across the TBM, comparing the finished machine with its original 3D digital design. Engineers work with tolerances measured in fractions of a millimeter because a tiny alignment error could affect kilometers of tunneling. The machine must be almost perfectly round before it ever reaches a construction site. Artificial intelligence now becomes one of the factory's most valuable inspectors. High-speed cameras capture thousands of detailed images every second while AI software instantly compares each component with digital reference models. The system detects scratches, surface defects, missing bolts, and dimensional variations long before a human could notice them. But here's what nobody tells you: AI still isn't perfect. Despite all this automation, experienced engineers still perform the final inspections. They run their hands across critical surfaces, listen to unusual sounds, and notice tiny details that even advanced computer systems sometimes overlook. Years of experience allow them to recognize problems that don't appear in digital reports. In the world's most advanced factories, human judgment still remains the final authority. With inspections complete, the entire machine comes alive. Hydraulic cylinders extend with enormous force, electric motors begin turning, conveyor systems move, and hundreds of sensors stream live data into the control room. Engineers watch every pressure reading, vibration level, temperature, and electrical signal to ensure every subsystem performs exactly as designed. The factory suddenly sounds less like a workshop and more like the control room of a spacecraft. Before the TBM can leave the factory, engineers simulate real operating conditions. The cutter head rotates while hydraulic systems generate enormous thrust, testing the machine as if it were already deep underground. Every vibration, every sound, and every temperature change is carefully recorded and analyzed. This is the closest the machine can come to digging a tunnel without touching real rock. Only after passing every inspection does the tunnel boring machine receive final certification. Detailed inspection reports, material records, welding documents, and performance tests are reviewed according to strict international engineering standards. Thousands of pages of quality documentation accompany the machine before shipment. Every signature represents confidence that this engineering giant is ready for years of work beneath the surface. The factory doors finally open, and the completed tunnel boring machine begins another remarkable journey toward its construction site. Soon it will disappear beneath cities, rivers, and mountains, where sunlight never reaches and failure is never an option. Everything you've seen so far has been preparation for this moment. But the real story begins when this colossal machine starts carving a path through the earth itself, and the scale of that challenge is almost impossible to imagine. Global facts. The tunnel boring machine you have just watched come to life represents far more than a single factory's achievement. Around the world, dozens of manufacturers build TBMs for projects that reshape cities, connect countries, and push transportation deeper underground. Together, this industry generates billions of dollars every year while employing tens of thousands of highly skilled engineers, technicians, welders, and machine operators. What looks like one incredible machine is actually the result of a global engineering network. Today, the world's largest TBMs are designed and built primarily in China, Germany, Japan, Italy, and Canada. China now produces the largest share of tunnel boring machines, supplying major infrastructure projects across Asia, Africa, and the Middle East. European manufacturers continue to lead many custom-built machines designed for extremely challenging geological conditions. Every country contributes decades of engineering knowledge to push tunnel construction even further. The global tunnel boring machine market is now worth several billion US dollars and continues to grow as cities expand underground transportation networks. New metro systems, railway tunnels, water diversion projects, and utility corridors drive demand every year. Some custom-built TBMs cost more than $50 million before they even begin digging. Imagine building a machine that costs as much as an entire passenger aircraft before it performs its first job.